All right, we're going to look at this problem where we have a block being released from rest, and we're going to look at what happens to it, well, how fast it's going as it gets to point B and to point C. Applicable chapters, that's chapter 7, conservation of mechanical energy. Coordinate system specified. No, we're not going to need that for this problem. Symbol of what we're trying to find, that would be V sub B and V sub C. Those are speeds. I know that says V, but V is not for velocity. It's not the vector form of it. It's the magnitude of the velocity, because in this equation for, well, it's not shown on the screen, but in the equation for kinetic energy, it's 1/2 mv squared, and that V stands for the magnitude of the velocity, which is also known as the speed. Speed and velocity both have units of meters per second. All right, so one of the things we need to do is define our initial state. So the initial state here is going to be at point A, and there's three things that we want to use to define our initial state: the height, the speed, and how much the spring is compressed or stretched. Okay, so this is going to define our initial state. The height, well, we need to know what we're defining the height relative to. We could draw a dashed line right across here, or we could draw one right across here. I think we'll draw it right here, and that way it'll be useful in the whole problem. That's the lowest it ever goes. So this is our h equals 0, is right on that dashed line. So that means our height is 36 meters. Velocity is 0 because it was released from rest, and there's no springs at all in this problem. All right, final is going to be right here, and so h sub b is going to be 16 meters. V sub b, I don't know, and delta x b is equal to 0. So now we can go about planning our solution. All right, so here's the equation. Gravitational potential energy initial, that term is going to be in there. The next term is spring potential energy, and that will not be in there because there are no springs in this problem. Kinetic energy initial, that will not be in there because it's starting with a speed of 0, says it's starting from rest. Work by non-conservative forces. This one's a little trickier. At any point along the path, we can draw a free body diagram which would have the normal force and the weight. And then if we were to draw the work diagram, well, we would not need a work diagram for the weight because that's a conservative force, but for the normal force, if we were to draw a work diagram, the, let's see, I'm not sure, I'll put it down here, work diagram. The normal force is perpendicular to the track, and the track is parallel to the track. In other words, the displacement is parallel to the track. And so at all times, these two vectors are going to be perpendicular to one another. And if they're perpendicular, that means the work by non-conservative forces is 0, because the normal force is the only non-conservative force in this problem. Gravitational potential energy at the final state, which is point B, that is going to be some. So we're going to have some in there. No springs at all. And we are trying to find out how much kinetic energy it has at the end. Well, really, the speed, but that's related to the kinetic energy. So now we can write this in. We can say mgha equals mghb plus 1/2 mvb squared. Now we look carefully. There's mass here, mass here, mass here. It's in every single term. Be careful, sometimes students will try to cancel out the mass when it's in 2 out of 3 terms. But that doesn't work. It has to be in every single term, so we can divide through by the mass. Now we can substitute numbers in here. 9.8 meters per second squared times 36 meters equals 9.8 meters per second squared times 16 meters equals 1/2 VB squared. And then we'll do the algebra here real quick. We'll go ahead and plug in some numbers. 9.8 times 36, 352.8. What are the units? we've got meters per second squared times meters. We get meters squared per second squared. And then on the other side, same units but different number. It's going to be 156.8 meters squared per second squared equals, plus 1/2 v squared, and then we subtract 352.8 minus 156.8, we get 196 meters squared per second squared equals 1/2 v squared. We multiply both sides by 2, and then we take the square root, and we get 19.798989. In other words, 19.8 v 19.8 meters. Well, what are the units? We're taking the square root of meters squared per second squared, so we get meters per second. All right, and that is the answer that we were given, so that's a good sign. Is the solution complete? Let's see. We're supposed to find the speed at points B and C. So no, the solution's not complete. We need to go back. All right, let's look here at point C. So I'm just going to write these down here at the bottom. The velocity at C is an unknown. The height at C is 0. And the spring, well, it's non-existent. So we don't have to worry about that. The equation stays pretty much the same, except that we're also going to cancel out this term. And so then when we bring this over here and we apply it A to C, okay, we could have, now there's two different ways you could do this. You could apply the conservation of mechanical energy equation from B to C, so you could use this newly found velocity at B. So you could go with this as your initial and this as your final. But I like going from A to C for two reasons. One is I don't have to worry whether this is correct or not, and whether that's going to mess up my answer to part C. But the other reason is that it's going to be easier. There's going to be less terms because there wasn't any kinetic energy at point A. And so then my equation is going to very simply be mgha equals 1/2 mvc squared. Divide both terms by the mass, and then we can very quickly plug in our numbers, and then we can simplify it down, and we get 26.6 meters per second. I'll let you check my math on that. Maybe I didn't round correctly. You go ahead and take a look. Now our solution is complete. We did get positive answers for our speed. Speed is a scalar, magnitude only. We did pay attention to our units. Remember here where we looked at meters per second squared times meters, got meters squared per second squared, took the square root to get meters per second. So the units made sense. And are the magnitudes of the answers reasonable? Well, this is pretty fast. This is like 40 miles an hour, and this is like 55, 60 miles an hour. So that's pretty fast. However, we're talking about a block that slid down a path with no friction, no air resistance, and it went downhill over 100 feet. So yeah, it's going to be going pretty fast if there's no friction and it went downhill that much. So that makes, at least, it's not crazy to think that it would be going pretty fast. All right, now let's look at the energy bar chart. Okay, and actually, let's make sure we just define how we're going to do it. Are we going to go A to B, or A to C, or B to C? So let's look at A to B. So make sure you label that. Did it have kinetic energy initially? No, that was 0. Did it have gravitational potential energy? Yeah, it had a lot. Had a lot of gravitational potential energy initially. So put a big bar in there. Let's see, that's 1, 2, 3, 4, 5 lines high. No spring potential energy. No work was done by non-conservative forces, as we talked about before. Kinetic energy. Well, it had some kinetic energy. And then, what about gravitational potential energy at the end? This is at point B. Okay, so this is, initial is A, and final is at point B. Okay, so here we'll just change that a little bit. There we go. So at point B, did it have gravitational potential energy? Absolutely. Can we just put any amount in here? Well, not exactly. What we need is for this plus this to add up to all the stuff over here. So we got 0, 0, 0, and then this is 1, 2, 3, 4, 5 bars high. And then we look over here, 1, 2, 3, 1, 2. So that adds up. We can even put little numbers in here if we want. There we go. So we see 5 is equal to 3 plus 2. So that does make sense. 5 equals 5. Perfect. All right. And that's how you do that one. If you did it from A to C, it would look a little different because there would be no gravitational potential energy here, and then this kinetic energy would be a 5. And that's just a relative scale. If you had picked this different, then you know, there's multiple ways to do this. It could have. It just depends what you pick. The important thing is that in the end you show that it has some when it does, show it 0 when it's 0, and that the total amount over here on the left adds up to the total amount over here on the right, just like in your conservation of mechanical energy equation.